Hi everyone, welcome to MathSpellBook. I'm your host Peter, and basically we are going to get back into some ODEs in addition to basically do a little research on PDEs. Now when I say research, I mean just a little bit of like learning a little bit about them. So when I say research, it doesn't mean like oh, we're gonna go in depth and like do like complicated stuff like you see like in university and stuff. No. I'm talking about just like studying up on that material. So hopefully you guys are doing well. It's Tuesday. Okay, so I think we're gonna still continue on with a little bit of the Laplace transform problem. So we're gonna do the ones involving just looking at the tables. So let us continue on with that. So we have this problem. So the first problem for this would be 1 over s squared, then minus, so we have a 2 here. I don't think that's, because I think for E it probably might be the same thing. So let me look at the table for E, because I think E is supposed to be E and then like KS or something. So, oh no, E is totally different. Minus A. Okay, so I gotta remember that. So I think like we're gonna have a 2 on top here. So, and the A is supposed to be 3. Okay, so I'm gonna have to remember that. So basically, E is gonna be 1 over S minus A. So I think that is our solution there. All right, for C, we have T. So I'm guessing we're gonna have to think of this as like sort of like this. Now I know that sine and cosine, they almost look similar. It's just I gotta remember exactly what it means, because I think it's supposed to be, it's either S minus A and then either A or S is on top. I think like that's how it's supposed to look like. What does the table show? For cosine it's S and okay. So what do we have? So we have to remember that for cosine of T, or cosine A of T I should put, actually. That makes it more specific to our purposes. So cosine is S squared plus A squared, and for sine it is A over S plus A squared. Okay, so in this case we have, so it's supposed to be S squared plus 4. But in this, but also we have to take into account this part. So S, and I think that is our solution. Hopefully like we'll get more of the same ones, so that way we can start to remember more about how to do these problems. Because I don't know if you guys have experience where, like, if you guys are doing like differential equations, like, does your teacher make you memorize these, or do they let you use a table? cosine. So for sine we have 3s plus a, and that multiplied by s. Oops. This should be 9, so it's 9. So that would mean we have hopefully solutions here. Alright, so okay, so we got B right. What about C? Double angle formula. So they want us to use the double angle formula in this case? Huh. Okay. So I guess we got this one not right. Because according to the solution, it seems that they want us to use the double angle formula for this case. Meaning so this is not the correct way for me to think about it then. We probably got some of these problems wrong then. Because I thought like with just the parentheses, but of course with trig functions you have to be very, very careful. So according to what they did, they want us to do the trig identity. So this has to be cosine 4 plus 1 over half, and then you take that out and you're left with t plus 1, and because of that so we're left with sine. So cosine is this s plus 16 and then plus 1s. So so let's see about D. way they wrote D is just trying to understand it, because the way they wrote it was because they wrote it like this, and I'm trying to understand why it's like that. The problem we have here in D is T. And the way they wrote the solution. Did I get the... That's the correct format for T, for the S format. I'm just wondering, why is it this? Wow, they're using a lot of trick identities for this one, because this one is also wrong. That's the one thing about like trick identities, they're very sneaky. But then again, like sometimes you just don't know how many trick identities you're supposed to know, or how much is supposed to be implemented. This is incorrect. Did we get E right though? Oh, we actually have to factor this out? Oh my gosh. So we didn't get this right either. I was hoping I didn't have to do that. I guess we have to. So we'll just erase this. Yeah, so these problems we didn't get, that we didn't do too well, because I think for me I was just trying to skim through because like since it was in parentheses, I thought, oh, we can do it within the parentheses. Nope, I don't think that's gonna work. I mean, at least we got B right. What is it that I'm doing wrong here? Do we have to do like a product rule or something? Because I'm wondering where they got this from. not thinking of this correctly? Because, like, there's something up with products, like, involving these. Like, the way they show the solution, I'm trying to better understand what they mean here. Are they trying to, like, turn it? Like, is there a different table for that? No, I don't see one. There's no table for E times, for T times E of T. Because we got E of T right, but I'm just wondering what happened to the transform involving T. That's the one thing I'm not understanding here. Because the answer is this. And I'm wondering why is... Because the T is multiplying by the E, is that why it's like that? That's the only thing I can think of, because when we think of T, we usually think of this, and when we think of E, we think of this. So is it like the T is kind of swallowing up the E here? Kind of like taking the E's properties but turning it into this property? That's the only thing I can think of. But I think we gotta do more problems to confirm that. So let me see. Let's try a similar problem. Oh yeah, we should open Quizlet too. So let me just open Quizlet. This textbook is the fundamental. Oops. Fundamentals of equations and boundary and value problems. Boundary value problems. Textbooks. I think this is the edition we're working with. So put in our. I know it says a physics folder, but put the plus transforms here. So that's the original definition. Now I'm just going to look for a question. Use the table. Okay, here we go. Let's see if we can look for something similar. Okay, so okay, here's one. We can try 15. So oh, that's 17, but we'll try it. Give us more practice. Because I think I have an idea of why it works that way, but I don't know if that's how it's set up that way. So in this case, so if the product in front is supposed to influence here, so that means if E is a 3, if that's supposed to become S minus 3, and then sine, if it's sine 6t, then that's going to become 6 over S plus 36. Now, since we have an S here, my theory is that the way this works is that it's just a theory, but it's the best I can think of right now. It's like turns this into this, and then we have this. So 3 times 2 is 6, so 6 over S plus to the 4th, and then this one will just be left with 1 over S minus A, minus 1. Now, I think we can just work a little bit on this, so can make that nicer by flipping everything over like this. Okay, so according to my theory, that's how this first term is supposed to look. Now let's see if I was correct. So I think the problem we did was number 17, right? Yeah, number 17 on chapter 7.2. So 7.2, right? And the exercise is 17. Okay. Let's see how did I write the problem right? Yeah, I believe so. And the table, yeah, the table we wrote for E is correct. And then for sine, yeah, that is correct. So let's see what the way they did it. So they had 6 over fascinating, because the way they did it was, so the E here, they put it in the S spot in this expression. Very interesting. Maybe I have to read up a little bit more on how they do this. So let's see if we can find it. Let's see if we can find an example of what they did. It's not a constant. Because for the last one, for this one, we had E, and this E went into this operation here. So this one was in front. The E's in front, but then it made it. Oh, wait a minute. No, the E's in the back here, and then the T's. Oh, okay. So apparently it works a different way. So it's not just front and back, it depends on like what makes it easier? Maybe? Let's see actually how we got the other parts. Yeah, the other parts are correct. Yeah, the other parts are correct. It's just this part. Very interesting. So, how do we interpret that? Okay, here we go. Let's look at this. Here. Exponential order of alpha. Okay. A function that is a piecewise continuous finite. However, piecewise continuity. So a function is said to be exponential order of alpha. There exists a positive constant t in m such that. For example, okay, here we go. This is something we can look. So it's less than or equal to. It holds when m is 1, and then t for any constant. So I guess for a trig function, it makes it less interesting. I guess it's because it's like a it has like a what do you call it? Like it's a, I don't want to say cyclic, but it's sort of like a back and forth type of rhythm. Check to make sure that we're streaming. Oh yeah, I think we are live. Okay, cool. That's fascinating. I mean, it does make sense because like sine goes from 1 to like 0, like back and forth, or 0 to 1, sorry, back and forth. So I can see why it's less than like the exponential that it's being added to. But that is very interesting. The more you know, right? Oh, this is a mathematical proof of it. Okay. So So according to that logic then, let's try problem 20 then. Because let's go with that logic and see. And I think we can try 19 after that. So this is... So we didn't do this problem right. But I think we're starting to get an idea of what we need to do for these type of problems. I think we can where's the delete? There we go. So we'll just backspace it. We'll paste this one. Okay, so let's just try what we observed. So according to, so we have +2 for E, and then for cosine it's supposed to be S over S squared plus 3. So if we take what we saw in the last problem, it should be S2 to the second plus 3, then minus, okay, so the last time we did this, so if we remember that this one, so this would be 2 on top, and then we'll be having 3 on the bottom, t to the power of 3 here, and then for this one is the same thing as this one. So if that's the case, then it will be like this. That's based on the logic that I can draw from for this. So let's see if our guess for 20 is correct. So this one's number 20. Table of contents, nice. 20. That's the same problem. Okay, cool. Because sometimes like Quizlet is kind of like iffy with certain additions. Sometimes I think people put problems from a different edition in where they're not supposed to. Okay. Hey Sascha, how's it going? What's the best part of your day so far, my friend? Oh, fascinating. So they added a +2. So we were close, but why did they add a +2 on top? I thought we were close to like actually finding out how this works. Oh, because it's an S. That's right. Okay, so everything with S is okay. That probably makes a lot more sense. So the S always goes on top here. But I forgot that that was S and not A. So the other side. Oh, whoops. Okay, so I think we have an idea of how this works. So for trig functions, you have to sort of treat them as like they're the shell for this one, because they cycle back and forth between 0 and 1. Whilst if you have just a a constant variable with the power with e, you have to kind of treat this as the shell for the exponential. Went to a nice math talk. Nice. What was the math talk about? Did it inspire you to get into deeper ideas? Like, what was it about? I'm kind of curious to know. So, okay, so I think I'm starting to get an idea of how these relationships work. So I guess the product of two Laplace transform entities, it depends on what they are. But that's a pretty interesting, that's something new we learned. So if it's basically a variable with a power to e with the variable, then I guess we have to put e into the actual placement of s in that port. Whilst in this one, like if it's a trig function, then we have to do the opposite, and we treat the trig function as sort of the outer shell for this one. Okay. That is fascinating. I wonder if there are any more problems like this. That way I can practice it. I hate it when I guess it, when I actually figure it out, but then there's no more problems for me to practice involving the same type of thing here. Oh, we could do 19. There. That's similar. So analysis results about pseudo effect class use. Oh, okay. So it's just basically analysis. Interesting. Okay, so we got this one. So let's practice this one. So we got t to the 4, which means that it's going to be s to the 5th, and then it's going to be 4 factorial. So 3 factorial is 6, and then basically 6 times 4, that would be 24. And in this case, we also have e to the 5th, which is 1 minus s. So together, they would form 24 s to the 5th, and we have e to the t, which is 1s minus 1. Well, Keller geometry, but the guy was doing geometric analysis. Oh, okay. Did you come up with any new ideas while you were listening to the talk? Find any connections that kind of sparked your interest? 7t, and this will lead us to s over s plus 7. So together, that would make this s1 squared plus 7, and the Laplace transform of that would be 24 s minus 5. Let me erase that. And then that's minus s1 minus 1 s minus 1 to the 2nd plus 7. Okay, based on our understanding on how we think these problems go, I think that's how it's supposed to look. So 19. Yep, that looks like the same problem. Alright, let's take a look. 24 to the 5th. Minus 1. Yep, that is correct. I wonder... They also have a boundary condition. I didn't notice that. For s is less than 5. Oh, because it can't be 0. Okay, gotcha. That's why they have that there. Okay, so now we're starting to figure out the pattern. Okay, is there any more we can practice? Like any interesting ones? I think 16 we haven't done. Actually, we can do 16 and 17. I mean, like, 17, I'm, like, barely remembering the answers, so I think we can do that. Well, actually, we can do 15, 16, and 17. I think that would be good. So, we'll copy all this. Go down here. Hopefully my progress is in this subject is, like, okay. Okay. Well, it was more about learning about new results, a little bit on the techniques he used to get those, but it's not that related to my current interest. Oh, okay, gotcha. I mean, yeah, you never know. Like, sometimes separate subjects will... Let's do 15, so we have 3 to... So it's going to be s to the 4th. And then this is going to be the 6. So that one we don't have to worry about. So we have t, and so the next term we're going to have t and e. This one's going to lead us to... Actually, this should be an arrow. This one's going to be s to the 2nd. This is going to be s minus 1. And together... They should make s to the minus 1 squared. And the next one, we have e to the 4th. That's going to lead us to s minus the 4th. Or minus 4, I should say. And then we have cosine t, which is s squared plus 1. Meaning that combined together, they will give us s minus 4 to the 2nd plus 1. So altogether, 15 will give us... So the first one is 3. So this one, and then is that a minus sign or a plus? Yeah, that's a minus sign. So minus that, and then we have a plus s. Okay, let's check if that is our correct answer. So that's number 15. So table of contents, 15 please. S to the 4th, s to the 2nd. Yep, that is correct. Cool. Okay, we're progressing pretty well. That's probably going to be the one thing about Laplace transforms that I'll forget if I don't practice. Just the way the maneuvering works. So this will lead us to S3, and then that will be 2, and then after that, that will be 3. So 3t equals to 3 over s to the 2nd. Then we have okay, so in this case you have e, we have e to the 2nd. Because technically we can take out the 2, but I'll just leave it in. So the 2 is s plus 1. And then, actually the 2 will make it more difficult. So we'll multiply the 2 afterwards. So we'll just leave it at 1. And then sine of 3. So sine of 3 is going to be a over s2 plus 9. So in this case, them put together, and I think we'll just put 2 for both sides. That's probably not a great way to illustrate it, but we'll just put it that way. So since it's 3, if we multiply by 2, that would be 6. So then s1 plus 9. So altogether, the linear transform will be s3 is it all minus? Yeah, it's all minus. So minus 3 to the s to the second power minus 6 plus 9. Okay, let's see if that is the correct answer for that. This one is, I think it's 16. So 16. Yeah, that is the question we got. So let's see. So 6. I think that is what we wrote. Yep, that's what we wrote. Okay, so I think I finally understand the way we're doing this now. Okay. So whenever it's like a trig function, we have to take this into the inside, and when it's like a constant, well, not a constant, but like a variable, like if it's just the variable to a power, we just basically incorporate the variable as the shell for this one. So, okay. And when I think about it, it makes more sense because when it's just a variable to a power, it's just basically multiplying it and it's adding more to e. But when it's like sine or cosine, it's kind of it either goes to 1 to 0. So that makes sense. Okay. All right. So for 17, let's just copy this because I don't want to keep scrolling back and forth. So 17. So let's do this correctly now, because I think we got it wrong last time. So 3 to the third, that will be s minus the third. And then we have sine 6, and that will become 6 over s squared to 36. And then we have t to the third, which will turn into s to the fourth, and that will be 6 on top. And then we have e to the t, which will turn into s minus 1. So altogether, oh, we have to combine these two. I don't want to forget that part. That's the most important part. So we have 6 to 3 minus plus 36, meaning that the linear transform, the Laplace transform, sorry, the Laplace transform is and then that minus and plus okay. 17 again. Oh, thank you for the follow, Buskans. And if you're in the chat, what's the best part of your day so far? So we have 6 here. Okay. Yep, everything looks correct. Okay, so that's the deeper essence of Laplace transforms. So whenever we have two products multiplied together, or at least with the exponential function, we have to think about exactly how it's going to function within it as a product. So that's actually good to know. What other interesting things here? Which of the following functions are exponential order? Feels like they're going into more of the detailed stuff. Like technicals, I mean. Because I think with like textbooks, you're kind of like unsure about how to approach like certain problems sometimes, or like you don't know how much technical stuff you have to know before you actually go into the next section. That's like the hard part. So I think we did a fair amount of good problems there. I think now we can do inverse Laplace transforms. Oh, whoops! No, I don't want to show this sheet because it's part of a course I'm taking. I want to give credit to the person that made this, so. Okay, so now we're doing inverse transforms. So now, let's see if we can do the opposite and figure out how this works. So we got 3 and 4. So the way this looks, it looks like we got the linear transform of 3 times t to the 3rd. I think that's like an easy one. So for B, we got s to the negative. Meaning, if we were to translate this, it would be like that. Ooh. Very interesting. So if you just minus this, that would just leave us with a half. Yeah, that would leave us with a half. But okay, this one is a bit iffy though. Because according to the way this is phrased, it's telling us that it would be because I know it's not t, the square root of t. But the thing of it is that like, how do we? I guess we gotta turn this into a function that we recognize. Because I feel like, because the way it looks, we could say it's like, it looks like it's supposed to be like t to the square root of t, but I know that the square root of t also involves pi in it. So why? Why it involves pi, I don't know. It's like pi. Oh wait, it's like pi to that. It's like pi over 2s32. So this one's a tricky one, because it just is missing some things. That's the thing that makes it tricky, because it's missing the square root of pi and the 2 part, because like the way that this the transform is this. And I'm wondering if that's playing a factor here. Because I know if you don't recognize the transformation, you have to try to turn it into something else. I just don't know how to write this. Let me see what the solutions show us for this. Okay. This one's not right. Oh, okay. Forgot that part. Yeah, sometimes I don't look at like the details. Like I got so excited, but then I forgot it's factorial on the top. Oh, wait a minute. So if the So does that mean it's going to be this times this. Yeah, that looks about right. Yeah. Okay. I just had to fiddle around with it. All right, let's get some more practice in. So c to the fs plus. So I think we know what this one is. This one's going to be e to the minus 5t. Yeah, there's nothing else on it. Yep, that is correct. Okay, at least we remember that. So let's try d. F of s is equal to f minus 6. Okay, so I think with the practice we put in, so this is 1, and I think this one it will be, so it would be the square root of pi over, because t the square root is pi, square root of pi over 2 s32. So what I'm thinking is that it would have to be 4 with pi on the bottom, and I think we can write this nicer by making it 4 times, oops, for pi. And I think that's the correct one. This one's letter D. Yeah, that looks about right, because we got rid of the pi up here, and we got rid of the 2 over here, but there's a 2 up here, so yeah, that looks right. Okay, next problem. Okay, so we got e is equal to f of s 5 3s. Okay, so I think we got a cosine and a sine. And that's a 5. Okay. So my guess, this feels like this is 2 problems. So f of t. So I know this part, this has definitely come from a cosine or a sine. So this is 5, it's not s. So let me just write that a little bit much more. There we go. Now it looks like a 5. If we separate this, and I'm just gonna move the 3 out here, just so that it's not in our way. S to the third, like that. So my guess is that we're gonna have So I think this first term, it can't be like, I don't think it's cosine or sine, because cosine, it has an S, and sine is a 1, and no, a sine is an A, and we know that for cosine and sine, this term has to be like the square root of, has to be the square root of 9, which is 3, which means A has to be 3. So this one right here is definitely cosine. The one thing is this part. So, because if there was a 1 here, then it cannot be cosine or sine. So, maybe I have to look at the table. Is there anyone that has a term that is similar to this one? Or unless we have to figure out a way to manipulate it in some way. We might have to manipulate it in some way in order for it to be a term that we recognize. So let's just write what we know. So this one's cosine to the third t. We'll leave that for now. Now for this part right here, I want to make sure that I write this 5 correctly, because if I see it as an S, I might accidentally like mix things up, and the problem, it is 5, so we gotta try our best not to maybe it's 2 terms in 1, because let's say it is cosine though, because if it is cosine, then it has to be that this S term up here but the thing of it is that it would leave an S, not a number. So maybe it's sine. No, but then we have an A. I mean, like 9 minus 4 is... So maybe it's sine we're looking for. Because then we have a 3. And... no. Then that wouldn't give us 5 though. That's the problem. Unless it's 2 terms. Like we have, let's say we have like, no. Because then we still have to get this term, and it would have to be like, ooh, this one's very, very tricky. Yeah, the 5 makes it very tricky, actually. Because, like, if it's sine, like, the way my thought process is that if it's sine, of a t, right? Then t has to be on top and s plus a has to be here. And if it's cosine, then it has to be s. Now the problem is that I feel like it could be sine. The one issue is that if it's a, then there's no way they can combine each other to get 5. That's the one issue, because we have a 9 down here, and that would mean that this a is 3. Now, so I have to think about what terms go together, like that you multiply by 3 in order to get you 5. Like the difference, I mean. Because I think that's the only reason why you have 5 in this case. And they have to be multiples of 3. So if you have 3 times 4, no, like I'm thinking it's going to revolve around 3 times 15, and then you're going to have to do 3. If you do 3 minus 15, then, well, no, it would have to be like around, yeah, it has to be like 3. Because what I'm thinking is that it's going to be, like, my thought process is that it's going to be something revolve around a number m times 3 plus a number n. Well, not like plus, but I think minus, like minus. Yeah, this is my thought process. Like, basically, like, these two terms would multiply by our product here, and then their difference would make 5. Like, this is m and n. Like, I'm trying to figure out. Because there's no way we can get 10, because it's not 15. We can do 18. 18 may work. Yeah, I think it might be 18. So I'm thinking this could be 6 times sine of this, yeah, and then minus sine, yeah, because if you do 18, yeah, it's like 6 times, that would be 18, and then minus 3, that will give us, oh no. Shoot, I was pretty close though. Because that would give us 15, not 5. Dang, we were pretty close though. Because there's no way we can get 13. That's the one issue. Unless I'm thinking about this all wrong here. of it is that they have to multiply by 3. But how do you get 5 on top? That's the one thing I'm not getting. Unless... because there's nothing that multiplies with 3 to get 5. Yeah, I think I'm gonna have to look at what they have for the solution for this one. Because this one is a little bit tricky. Okay, so we got this term right. The way they wrote it was 5 times... Interesting. So the way they wrote it was 5 over 3 sine of 3t. Now I gotta look at the way that affects it. So if we have this, oh, okay, that's the reason. Okay, that was, dang, that's a simple solution. But sometimes I don't use Occam's razors that well. Dang. But then again, like, I guess like when you don't practice math a lot, that tends to happen. You forget these small little tricks that could be like right in front of your face. But, you know, it happens. It happens. Okay, well, that's something to, like, you know, to keep in mind. Because sometimes it could be just something very simple like that. And I realize, oh wait, it's simple. Why couldn't I figure that out? And usually, I think, like, I remember watching a video on, like, how to study once, and, like, the person, I don't remember who was, what channel it was, but I think it's a person that's really good at studying. They usually say that even though you make small mistakes like this, there's probably a reason why you keep making these types of mistakes. and I think when it comes to, like, these, like, mathematical tricks that I probably do have in mind, but I don't see it right away, there's probably a reason why I'm making these mental blocks. Okay, so what do we got here? This one looks very messy. So, let's see, we have 10s, 25, 2, and then minus 3, 25 minus s. I just split it up just to make it, I think, a little bit more manageable to see. So now we gotta actually think about how this is gonna work. So we got... Now we got a minus s squared. Now the question is that anywhere on our table? Oh, yep, it is. Well, something close to it anyway. For some reason, because is like this, and this one is like this. However, we have the S term as a negative in this case. Now my question is, if we change those to their inverses, would that actually affect it in some way? I don't think so. Well, I think I'll leave this problem for for a few minutes. I'm more curious about learning a little bit about partial differential equations. So I think I'll just learn a little bit of partial differential equations, just to let my curiosity burn the oil. Cause I started reading this book. I have an older edition of this book, but the section pretty much the same. So I wanted to read more about the separation of variables. Because it seems like in order to have a heat equation, you have to actually have conditions on it. You basically set it up like this, and I think the way to prove it is that you basically have these different parameters working in conjunction with one another. Because I think the thing that I liked about when I opened this book, I was like, oh, okay, I'm starting, I like the way it's organized, so I can actually see everything much better. Because I think with partial differential equations, the thing that's hard about it is that I think with with ODEs, you can look at the textbook and it will show you I think things put in sections like this, and then it's kind of boom boom boom. You basically look at the way they set it up and then a few examples, and then you're able to understand the method. But for partial differential equations, it's a little bit more involved. You actually have to know certain information about the system, and then you have to actually incorporate that into the math, and it's a lot of reading. It's a lot of definitions and terms and all that stuff, and I think that's why with partial differential equations, it feels as if you kind of feel you're kind of bombarded by a lot of information at the beginning, and you're I don't have any solid bullet points here. Let's see, develop a model of the flow of heat through a thin insulated wire whose ends are kept at a constant temperature of 0 Celsius, and whose initial temperature distribution is to be specified. Okay. Okay, suppose a wire is placed along the x-axis, x equals 0 at the left end of the wire, x is equal to L at the right end of the right end. Okay, so we have 0, and then we have x, and then we have x delta, x plus delta, delta x, and L. Okay. Okay, if you do know if you let U denote the temperature of the wire, then U depends on time and on the position X within the wire. Okay, that's about self-explanatory. We will assume that the wire is thin, and hence U is a constant throughout the cross section of the wire, corresponding to the fixed value of X. Because the wire is insulated, we assume no heat enters or leaves through the sides of the wire. To develop a model for heat flow through the thin wire, let's consider the small volume element V of the wire between the two cross sections planes A and B that are perpendicular to the x-axis, with plane A located at X and plane B located at X plus delta X. The temperature on A at time T is U onto X and T, and the plane for B is U X plus delta X and T. We will need to follow the principles of physics to describe the heat flow. Oh, I have that book. Let's see, heat conduction. Okay. The rate of heat flow, the amount of heat per unit time flowing through a unit of the cross-section A, is proportional to du over dx. Okay, so it's a rate of change from like the space or like the area, and the temperature of the gradient at A. Fick's law. Okay. Fick's law. Okay. The proportionality constant K is called the thermal conductivity of the material. In general, the thermal conductivity can vary from point to point. K is equal to Kx. Okay. Okay, so the direction of heat flow. The direction of heat flow is always from points of higher temperature to points of lower temperature. Okay. So the direction of heat flow is always points of higher temperature to points of lower temperature. Okay. All right. Specific heat capacity. The amount of heat necessary to raise the temperature of an object of mass m by the amount delta U is Cm delta U, where the constant C is the specific heat capacity of the material. The specific heat capacity, like the thermal conductivity, can vary with position. C and okay, so C is a function of X as well. If we let H represent the amount of heat flow from left to right through the surface A during the interval of time T, delta T, then the formula of heat conduction becomes, okay, A is the cross section of the wire. The negative sign follows from the second principle. If is positive, then the heat flows from right to left, hotter to colder. Okay. So does that mean if it's negative, then it will flow from cold to hot? I'm guessing, because it says like hotter to colder, so I'm guessing if it's negative, it's gonna go the opposite, where it's gonna be colder to hotter. Similarly, the amount of heat flowing from left to right across B during the interval time delta T is... Okay, that looks self-explanatory. The net change in the heat, delta E, in volume H, is the amount entering at NA minus the amount leaving NB, plus any heat generated by sources such as electrical current, chemical reactions, heater, etc. The latter is modeled by a term Q xt delta x A times delta T, where Q is the energy rate power density. See, this is a lot of like info. It's literally like a lot of info concerning the system. And I think with partial differential equations, you have to keep that into account. Otherwise, it's like you're kind of ignoring certain parameters. And I think that's why with applied maths, like if you're trying to like put in like, I think like a mathematical expression that basically describes the whole entire system, you have to think about like things like wind current and like air resistance and all that stuff, depending upon what you're studying, I think. Let's see, where is the change of in temperature, and C is the specific heat capacity. If you assume that the change in temperature in the volume is essentially equal to the change in the temperature at X, that is delta U is equal to U delta T minus and that the mass of the volume V of the wire is A rho delta X, where rho is the density of the wire. That, dang, that's like a huge amount. So, oh, okay, so you're supposed to set, so this specific expression, this one talks about the heat, flow. So this is the heat flow from A and B plus the amount of, what is it? Where is it? Oh, here we go. The energy rate or the power density, which is right here. And that's supposed to be equal to where is it? The net change of heat. Okay. So the net change of heat would be so these expressions are practically like equal to each other. They're like equivalent to each other, because I'm like, if E is equal to this, then why equate these two expressions for in a given equation 1 and 2. Okay, so make these like equivalent to each other. That means now divide both sides by A. Okay, by A, T, delta T, and delta X. So rid of delta x, delta a, and delta t. Then take the limits of delta x and delta t to approach 0. Okay. So this will be 0, this will be 0, and this will be 0. Let's see, if the physical parameters of K, C, and rho are uniform along the length of the wire, then 3 reduces to one-dimensional heat flow equation. Okay, that's what I was thinking. I was like, where did the beta come from? And like, where did these go if they're like uniform? So these would be divided into this one. And then these two would probably like end up together to form this. So OP is, oh, okay, so diffusivity I can't read that, materials, so I have to figure out what that means, and then we're given conditions that must follow. So it goes from 0 to x, that's one condition. T is always greater than 0. So when u0t is equal to ult equals 0. So this model is an example of initial boundary value problem. Intuitively, we expect that the equations 7 and 9 completely and unambiguously specify the temperature in the wire. Okay, so this is the heat equation right here. Now we got, here's the Laplacian. Do they show the Laplacian equation? When the temperature reaches steady state, it is, that is, when U does not spread over time and there's no source, then du over dt is equal to 0, and the temperature satisfies the Laplace equation. Excuse me guys, sorry. So I just wanted to read over a little bit of the heat equation so I can understand a little bit the mind process of how it works. So now I wanted to read this part, the separation of variables. Has a second derivative in it, or second partial derivative in it, second order, and this one's first order. So to solve this problem by the method of separation of variables, we begin to address equation 1. Suppose that it has a solution form this part, u dt, and for this part, okay, so they wrote it like this, and then they basically put the variables on one side and the other variables on the other. So they have to be equivalent to each other. Okay. Now observe the function on the left-hand side for depending on t, and those on the right-hand side depend on x. If we fix t and vary x, the ratio on the right cannot change. It must be a constant. Most authors define this constant with a minus sign, so we adhere to the convention. Wonder why? Maybe to make the math easier? Consequently, for separable equations, we have reduced the problem of solving the partial differential equation 1 for solving the two ordinary differential equations in 5. Oh, okay. So I guess they just turn it that way so you can make it into a differential equation. Okay, that is interesting. Next we consider the boundary conditions in 2. So number 2 we have, oh, here we go. Time is always 0. I mean above 0. So hence either t is equal to in these cases I think we're familiar with second order differential equations. And I think this one is a first order. Yeah, this one's a first order. So, I think this would probably be an integrating factor. So we got eigenfunctions here and eigenvalues. that's pretty cool. Because I think for these cases here, it's like in case like, you know, you get 2 roots. I think case 1 is like if you get 2 roots, then you basically get to so let me see what it is. Okay, yeah, there are 2 roots. Okay, just want to make sure of that. And I think case 2 is when you get like 1 root, and case 3 is when you get like an imaginary root, where it's like you have to like do this type of scenario. Actually, if I didn't learn that much about, if I didn't learn this part in I guess like the crash course in differential equations, I probably wouldn't have understood this part. So I'm kind of thankful that I was able to understand that part. Any knowledge is usually worth worth something. Let's see, the time boundary system. Okay guys, I think I'm going to end it a little bit early because I think like my body's like telling me it's like we're reading too much into this and like it's starting to get worn out. And plus we did a good portion of problems here. Like we didn't get all of them right, but at least we learned something about the behavior behind this linear transform and how to actually solve it efficiently. So I'm kind of grateful we actually got to that point. But I think today that we got a lot done. We learned a little bit more about Laplace transforms. We started doing a little bit of inverse Laplace transforms. So I think that is a win for today's study session. So I know it's like I'm ending a little bit early, but it's like whenever I put my head in a book, like at least like trying to get information, I'm trying my best to like actually like absorb it all. But you know, sometimes I guess like when like I read too much, like your brain just gets a little bit heavy with all of that. So thanks for joining me today, guys. We will be back tomorrow. So if you like math, physics, in addition to like, you know, you need a study stream to keep yourself productive and whatnot, and you need just a little background noise, if you're watching this on YouTube Live, consider dropping, like, you know, hit the subscribe button as well as hit a like for the video. And if you're watching this after the YouTube live stream, you know, drop a comment down below and tell me like what, if this helped you, or what projects you're working on, or like what subject are you studying for. Anything to like basically keep you guys engaged. In addition, all the links are in the description down below for the Discord as well as my gaming channel as well. I will be doing a stream on my gaming channel as well, but that's going to be like much later in the night, probably like around like 11 p.m. Eastern time. For all those on Twitch, you know, if you like math, physics, and or a study stream to keep yourself busy, whether it be an art project or something like programming or something, or just something you just need to like turn on to like make yourself productive with the assignments you have on the computer, consider dropping a follow. Okay guys, today was a lot of fun. We actually got a lot of knowledge down. But thank you very much for joining me today, guys. We'll be back tomorrow, and always remember, everyone is precious. You guys are just as precious as everyone else, and I will see you guys in the next stream. So take care, guys. Bye-bye.